All right. Well, hey, everybody. So we're going to talk about DNS, the domain name system. We've mentioned it, talked about it a little bit, started these slides. So I'll be going through the first 5 or so fairly quickly. Just to review, the purpose of DNS is to allow human digestible, readable, pronounceable names and assign those to IP hosts. So it's basically a mapping, mapping a name, domain name, to an IP address, where the IP address can be IPv4, IPv6, and we've learned with our use of the getAddrInfo system call that a name, a domain name, might be assigned multiple addresses, so multiple IPv4, multiple IPv6 addresses. The original DNS system was really not much of a system. It was a flat file, probably maintained by one or a very small number of people, did not scale well at all. And so DNS was developed for scalability as one of the primary goals. It scales due to two aspects. One is the hierarchical nature of DNS, and two, the caching that's name servers are able to do also enables or promotes scalability. So a domain name consists of labels separated by periods, and a label can be large, up to 63 characters, and an entire domain name can be very large, can have up to 255 labels, but the larger the label in terms of characters and the number of labels sort of defeats the purpose as those numbers get high or large, because DNS is to help simplify our use of being able to identify specific hosts. Built within the domain name is the hierarchy, and so the top of the DNS hierarchy is at the furthest right. So it ends in .edu, okay, but a fully qualified DNS name, domain name, is actually terminated by a dot at the end. So we normally don't show that, but if we were to look at within a program at the character string that contained the name, we would see that the very last character is a dot, which represents the root, so the top level. edu represents the second level. Actually, terminology, the edu is referred to as top level domain name servers. Oops. And then in this example, Clemson would be the next lowest domain in the hierarchy. And there's a CS there, which today might need to be converted to computing, but that represents the next level in the domain, and the www is is really a no-op, and we'll try to explain that later on. Okay, so the client code, which runs on all TCP/IP hosts, is called the resolver. The programming interface to the resolver, we can get to it in a couple of different ways. For the most part, we'll always use getAddrInfo as the primary interface to the resolver. So that was the code that we have seen. For example, all right, so I'm in our code directory, and we have a number of subdirectories here. In simple UDP echo, that was the very first UDP client server that we looked at, that pretty much was straight from the Donahue chapters. It included a program called getAddrInfo, which consists of a single C program. So getAddrInfo, we provide two parameters, the name, domain name, and the service or port number. And we are preparing here to call getAddrInfo. So there's the call to getAddrInfo. We're going to pass it the domain name, the service or port number, so both as strings, character arrays, or pointer to character arrays. Then we're going to pass it two references, two pointers to a struct that is referred to as addrInfo. And so we call the first one addrCriteria, and that parameter is for our purposes, it allows us to provide hints to the system as to what type of address we might be interested in. So for example, we could say, rather than address family unspecified, we could say AF_INET for if we only are interested in IPv4 addresses, or we could specify AF_INET6 if we're interested in only IPv6 addresses. The important thing that's returned on getAddrInfo, it's going to fill in addrList. Okay, so above we should have defined a variable called addrList, and it's right here. So it is another struct addrInfo, rather a pointer to, and so the result of calling getAddrInfo is the system is going to create an addrList or an addrInfo struct and return the pointer in passing that into our pointer. So addrList will point to the returned information from getAddrInfo. Okay, and so this is example code here where it walks through the struct, and so we'll do a man of get adder info, which will show us the fields of adder info. But the main idea here is that what's returned is actually a linked list of adder info structs. So each adder info struct in the list contains an address that is being passed back to us from DNS. And let's take a look at that struct. So if we do a man get adder info, so this is the struct adder info, and we see fields that contain that include flags. So we'll look at some settings that might be of interest that we might set in the flags field. Family is, as we've talked about, AF unspecified or AF underscore INET or INET 6. Socket type protocol, it's specifying the length of the address, and then it's passing back a pointer to a struct sock adder. And if you remember, the struct sock adder is the generic sockets struct for representing a IP address. It could be a v4 or a v6, and our code needs to be aware of if it's a v4 or v6. It's the canonical name is returned. So when we specify, for example, if we had called get adder info, the program passing the parameter www.google.com and the service of HTTP, it would return a number of adder info structs linked together, and each might contain a canonical name, which effectively would be another name that can be used in the same way as the domain name that we passed in on the call to get adder info. And then finally, the last field, struct adder info, AI underscore next, is the pointer to the next struct. If that's null, then this struct adder info is the last one in the link or in the list. All right, let's see if there's examples of the flags. Okay, so there's flags such as AI passive, which is something that a server might do when it creates its adder info struct before it does a bind, because it's effectively doing a passive open on its socket. An active open would be typical of what a client would do, where it opens the socket and readies the IP address which would be the attr_info struct, with the information related to the server. So let's go back to the slides and sort of continue on here. So the client code would be interacting with the resolver, whether through get attr_info or there's other system calls that would get us to the resolver. Other components within DNS, there's name servers. So each level in the hierarchy that is sort of encoded within a domain name, each level would require, or each domain would require a name server. A name server is basically a host so it's a TCP/IP stack running the DNS software, which allows it to perform the task of a name server. A name server needs to have at least one name or IP address of the root name server. And we'll look at the root name server sort of in the context of the larger DNS hierarchy that makes up DNS within the internet here in a couple of slides. A name server also maintains a cache. So when a client issues a query, basically the query is the client is asking to the name server, here is a domain name like www.mit.edu, and it's asking the name server to resolve that name, which means it wants a reply or an answer that contains the IP address. Once the name server answers, it's allowed to place that binding in its local cache. There's two types of DNS replies: authoritative, non-authoritative. So again, imagine a client issuing a query like www.google.com, and if the answer comes from a name server that owns the domain name, or in other words, the name server, the domain name is in the zone of authority of that domain, of that name server. So in other words, in our example, it's answered by Google name servers, then the answer is considered authoritative. If the answer comes from a cache, from a name server's cache, it is non-authoritative. There are two types of requests a client can issue: iterative or recursive. And the difference is in who does the work. So recursive would be, let's see if I have that. Recursive requests sent by the client. Okay, so recursive would be the norm, and a client requests recursive where the name server, its first hop name server, gets the request or the query, and that name server is responsible for completely getting the answer to the query. And so it will return back to the client either an answer or an error. Iterative means the client wants to do all of the work. So it asks the query to its first hop name server. The name server, if it's not able to answer, it will send back a pointer or a referral to another name server for the client to try. The client then would have to issue a query to that next name server. And so the entire process could take multiple iterations between the client and different name servers before an answer is found. Okay, DNS is a system that requires management entities that control the domain namespace and the registration of names to IP addresses. So we can't have two organizations trying to use the same domain name with different IP addresses. So there needs to be some entity that is in charge. And the Internet domain name is the Internet Society, so ISOC. And this is really the top level organization that runs effectively all other internet related organizations. So Internet Society is a real society. Any of us could join it. It's a fee, and you get access to certain information. Without joining, there's lots of interesting information available about the internet. So I encourage you to browse this site to just get a feel for what's available. So again, it's the Internet Society. One of the organizations that are managed or overseen by the Internet Society is ICANN, and this is the organization responsible for managing the address space. So that would be both IPv4 or v6 addresses and domain names. So their website, again, is a source of lots of information. The domain name portion of what they do is probably in several of these bullets. We'll look at INA services. Okay, so global coordination of DNS route, IP addressing, and other internet protocol resources is performed by this organization, the Internet Assigned Numbers Authority, INA. And so here is lots of information that is related to management of domain names, addresses, and protocol assignments. So when we talk about the IP protocol, we'll see that there's a field in the IP header called protocol ID. So in other words, an IP datagram can carry different types of content, and it starts with the choice or type of transport protocol. So the protocol ID in the IP header would specify, for our purposes, it would be one of three choices: UDP, TCP, or ICMP. And then the payload, or the user data, would be appropriate for that type of socket. So the application, as we know, when you issue a socket system call to create a socket and get the socket descriptor, you specify if you want the socket to be of type UDP, TCP, or something called raw socket, which allows a program to effectively build its own IP datagram. That is how ICMP messages are typically created. So the ping program, for example, would use a raw socket. Okay. So now we're going to go through an example of if from our computer, that would be somewhere on Clemson's campus, let's say, and then we issue, maybe we point our browser to www.mit.edu. So we want to look at the flow of DNS messages, which are going to be the payload or inserted into IP datagrams. We want to look at the sequence of flows that happens, and there's different possibilities. So this is just one example. Okay, so first case is our client, our host, the program starts and it uses the local resolver to issue a query to the local name server. And the easiest case is if the domain name, and so let's use www.mit.edu, is already in the cache. So the name server would send back an answer. It would be labeled as non-authoritative, and it would contain the any number of IP addresses that could be used to allow that application to access the web server at mit.edu. So that's the simplest case. Okay, the next example is the recursive request sent by the client, and we'll say it's www.mit.edu is not in the name server's cache. So there's the query. So recursive means the name server is going to do all the work. Iterative would be the other case, and the diagram would look different. So recursive means since this name server can't provide the answer, it needs to go to another name server. And again, as I said, there's different choices here. Here, it's going straight to root. It could have gone to the .edu top-level domain name server. In this case, going to root returns an answer which is going to actually be a referral. So it's not going to be an answer that contains the IP address that the client wants. It's going to be a pointer to another name server for the Clemson name server to try. And the pointer referred to in that answer is pointing to the .edu TLD name server. So our Clemson name server would then issue the query to .edu name server, which returns with an answer, again, not containing the address, but another referral. So it's going to refer our name server to MIT's name server. So now Clemson's name server issues the query to MIT's name server, and in this case the MIT name server and the name www.mit.edu is in the zone of authority of this name server. That means there's an admin person who has typed in somewhere that binding of that name to an IP address, and that answer is returned, and it'll be marked authoritative. The Clemson name server will place that answer in its cache, and it'll return the answer to the client, still marked as authoritative. All right, so this in words sort of goes through the three different possibilities. We've already talked through if the local name server has it in cache. So one further concept or term that need to introduce is the notion of a resource record. So answers are, whether they contain an IP address or a referral, are referred to as resource records. If the local name server does not have the name, okay, so here we split depending on if the client asks for an iterative resolution or a recursive. We went through the recursive case, and so being a bit more precise here, the answer that is eventually returned to the client is referred to as an A resource record. So it's a resource record that has a type A. A resource record that returns a referral is called a PTR resource record, or a pointer. Okay, two aspects of DNS. So one is the interactions at the local host resolver, and second would be the actual protocol, which defines the message formats and the rules by which name servers have to agree to interact and abide by. All right, so the local host resolver, I think we've been through this sufficiently. Basically, this is our interface to the resolver, which is get adder info. One point here, so you can manually enter a binding in /etc resolve.conf, and that's where you can specify the name server and the default domain /etc/hosts. You can actually add specific bindings. Okay, now the actual protocol. So we're going to get a feel for the message formats. So a DNS message can have up to 4 sections. A query, and then a response, which could be an answer, an authority, or additional information. So 3 types of responses, all of which are called resource records. Typically, in an answer, when you get a valid answer with an IP address, you'll see an answer, an authority, resource record, and additional information. So typically the authority resource record will contain the IP address or the name of other name servers that the client could potentially try. So for example, if the answer, which contains the actual IP address, is marked as not authoritative, the authority resource record would actually hold the name of the authoritative name server. The additional information typically would be either the name or the IP address that goes with the information in the authority resource records. So the client could use that to issue a query if it really wanted an authoritative answer. Protocol aspects, so DNS can use UDP or TCP. By default, it's UDP, and the protocol will actually deal with cases when a query or an answer is dropped in the network. So in other words, there's timeouts and retransmissions that go on. And that's that last point. If using UDP, DNS must do its own recovery. This is the message format of a DNS message. So the ID field would be a unique identifier that is helpful when issuing a query, because the answer coming back should have the same ID number. A parameter field has some, it's basically a bit field, which we'll look at here shortly. So for example, there's a bit in there that is authoritative or not authoritative. So that's where we find out things like that. There's a bit in there that is iterative or not iterative, and so that's where the client can set its preference. A field that indicates how many queries are contained in the message, how many answers, how many authority resource records, and then how many additional resource records. Then there's, depending on the number of each, there's that number for queries, answer, authority, additional information. Okay, so the parameter field that we described or identified in the message, so the first bit, the least significant bit, is indicating if this message is a query or a response. The next 3 bits, 2, 3, 4 bits, indicate if it's a standard query or an inverse query. Okay, standard means the query has a domain name and it wants the IP address. Inverse is just the opposite. We have an IP address and we want to learn the domain name. Okay. Why would we want to do that? Okay, so one example would be let's see, ping, and I hope this is correct. I think it is. If we were to issue ping and then an IPv4 v6 address, the ping client, when it gets a reply, would do an inverse DNS lookup, given passing in the query the IP address of the server and it wants to learn the domain name so that when it presents its information to the user, to us who started the ping, it would give us the result not using the address in numeric format, but using domain names. Bit 5, if the answer is authoritative. Bit 7, if recursion is desired. And then the last 4 bits, 12, 13, 14, 15, the last 4 bits would indicate no error or error. Okay, and there's several different types of errors that are possible. Okay, the format for a resource record. So the resource domain name, if this is an answer, then the domain name would likely contain the original domain name asked by the client, and we'll look at the type in the class, what that means in a second. Time to live is, if this is an answer, it's the name server that supplied the answer. It would fill this in with the number of seconds it would like the name server, the local name server, to keep this answer in its cache. So this identifies the lifetime of the cache entry. Then it's specific data associated with the type of resource record. And so the type is going to be specified in these fields, whether it's an answer, additional information, or whether it's a referral. Okay, final concepts here. So domain registration is sort of the process by which one would go through to get a domain name registered. So we can do this that has meaning within an organization and within the context of the internet. So here at Clemson, if any of us wanted to have a Linux server, for example, we could ask CCIT for a domain name. We would tell them, specify what the name is, and they would add that name and provide let's just call it a static IP address. It's, when we talk about DHCP, we'll be a little bit more specific, but so Clemson and CCIT can act as a registry for names within where they're the zone of authority. Or externally, we can go to a company that does this as a service. So like, I'm trying to think of a good example. Domain.com, mydomain.com is a registry. There's usually a small monthly fee to register a domain name, and then there's a couple of options, whether you are providing the name server or whether you would like the registrar or that service provider to perform the name server function on your behalf. And then finally, dynamic DNS. So when we talk about DHCP, I'll come back to this. So dynamic DNS it requires a service. So, mydomain.com or any registry would provide a dynamic DNS service, and some of them are actually free. So it also requires enhanced code functionality within your network, so that the thing that dynamic DNS is doing is, if normally a domain name is mapped to an IP address, and the original intent was it's a long-term binding, it shouldn't change, but in the world of broadband access, service providers might change the IP address of your modem, and you could use dynamic DNS to maintain a correct domain name mapping to the IP address of your modem, so the public IP address. And if your service provider changed that address, the code running dynamic DNS on the modem would send a message to the service provider you're using that's providing dynamic DNS to modify the entry and update the IP address. And that completes our discussion on DNS.